Hello viewers. So today we'll discuss some solved problems on Rolle's theorem. Viewers, I have already uploaded a detailed video on the concept of Rolle's theorem. Now today uh, uh, I am going to solve some problems which are based on Rolle's theorem, or will verify Rolle's theorem for some functions in the given intervals. So let me first remind you, or let us recapitulate what is Rolle's theorem. This is just for the viewers who have not watched my previous video. So Rolle's theorem says that if y equal to fx be a real function, and if it is defined in the closed interval a comma b, and if it satisfies three conditions. Clear? And what are these conditions? This function fx is continuous in closed interval ab. This function is differentiable, or f dash x or f prime of x, or the derivative of f exists in open interval a comma b, and the value of this function at point a and at point b is equal. Then there exists a real number c belonging to this open interval a comma b such that the derivative of this function at this point c is 0. That is, the slope of the tangent at this point c is 0. Clear? So let us start with this problem. I have already discussed in detail regarding Rolle's theorem in my previous video. So here we have to verify these conditions. So let us see the first one. See, we have fx equal to sine 2x, and sine 2x is a trigonometric function. And all trigonometric functions are continuous. So therefore fx is continuous in 0 to pi by 2. Clear? The second one is f prime of x, the derivative of f, sine 2x is 2 cos 2x, and it obviously exists in 0 to pi by 2. Clear? And the third one is, let us see f of zeros, because here a is 0 and b is pi by 2. So what is f of 0? F of 0 is sine 2 times 0, that is sine of 0, which is equal to 0. What is f of pi by 2? This is sine 2 times pi by 2, which is equal to sine of pi, this is 0. So we see that these two are same or equal. So therefore f of 0 is equal to f of pi by 2. Clear? Hence we claim that there exists a real number c which belongs to this open interval a comma b. Hence there must exist a c belonging to this 0 comma pi by 2 such that f prime of c is equal to 0. And viewers, f prime of c means 2 cos 2x equal to 0. So we have cos of 2x equal to 0, and we can write cos of 2x can be written as, since cos of pi by 2 is 0, so we can write cos of pi by 2. So 2x becomes equal to pi by 2 and x becomes pi by 4. And obviously this value pi by 4 belongs to this interval 0 comma pi by 2. Clear? Therefore the Rolle's theorem is satisfied, and we can say that this function fx is equal to sine 2x in the interval 0 to pi by 2 verifies Rolle's theorem. So let us take another problem. So here we have to verify Rolle's theorem for fx equal to x times x plus 2 e raised to x in minus 2 comma 0. Here we see that the first condition is we have to prove that this function fx is continuous in a comma b. So here we see that fx can be written as x square plus 2x times e raised to x. Now we know that x square plus 2x is a polynomial function, and this is multiplied exponential function. Clear? So here fx is a product of polynomial function and exponential function. So polynomial function is continuous, exponential function is also continuous, and we know that from an elementary result from limits, we know that if two functions f and g are continuous in their domain, then their product is also continuous in its domain. Clear? So here the polynomial function is continuous, exponential function is continuous, so the product is also continuous. So therefore fx is continuous. Clear? Now the second one. The derivative of f exists in a comma b. So let us find the derivative. So here f prime of x is, here we have the product of two functions, so we can write x square plus 2x times the derivative of e raised to x is e raised to x, plus then we have e raised to x, and then we have the derivative of x square plus 2x is 2x plus 2. Clear? Now if we take e raised to x common, we have x square plus 2x plus 2x plus 2. Clear? So we can write e raised to x square plus 4x plus 2. Clear? So we see that this is differentiable and this is differentiable. Here fx is x square plus 2x e raised to x, and we see that this function is differentiable in a comma b. Hence f prime of x, which is this expression exists in minus 2 comma 0. Clear? So therefore f of x is derivable in minus 2 comma 0. Clear? Now the third condition is f of a equal to f of b. So let us first find f of a, means this is a and this is b. Clear? So f of minus 2 is clearly we have minus 2, then we have minus 2 plus 2 e raised to minus 2. So this is clearly 0 because minus 2 plus 2 is 0, and f of 0 is equal to, and f of 0 is obviously, here we substitute 0, so it becomes 0 times 0 plus 2 e raised to 0, and it is clearly equal to 0. So therefore f of minus 2 is equal to f of 0. So we see that all the three conditions of Rolle's theorem are satisfied. Clear? And therefore we can claim that there exists a real number c belonging to this interval minus 2 comma 0 such that f dash c is equal to 0 and f dash of x is given by this expression. So here we can write e raised to c. Here we will substitute x equal to c because f prime of c is equal to 0. So e raised to c, we have c square plus 4c plus 2 is equal to 0. Clear? Now we can write we know that e raised to c cannot be equal to 0, so this factor should be 0, and we can write c square plus 4c plus 2 is equal to 0. Okay, now we can solve this quadratic equation here, and so here we can find the discriminant, that is d is b square minus 4ac. So we have 4 square minus 4 times of 1 times of 2, this is 16, this is 4 to the 8, that is equal to 8. Clear? So therefore c is minus b plus minus square root of d over 2a. So this is the formula, quadratic formula. So we can write here c is equal to minus b means minus 4 plus minus square root of 8 divided by 2. Clear? So here we can write c is equal to we can take minus 4 plus minus square root of 8 can be written as 2 square root of 2, and this is divided by 2. Now taking 2 common, we have minus 2 plus minus square root of 2. Clear? So here we see that we have two values. One is minus 2 plus root 2, and other is minus 2 and minus root 2. So here we see that if we substitute the approximate value of square root of 2, we see that square root of 2 is 1.414, and if we take minus 2 plus root 2, so we have minus 2 plus 1.414, which is equal to, so we see that minus 2 plus square root of 2 is minus 2 plus 1.414, and we have this equal to minus 0.586, and which obviously belongs to this interval minus 2 comma 0. Clear? And if we take this value, we see that this is minus 2 and minus 1.414, and this is equal to minus 3.414, and this does not belong to minus 2 comma 0. So hence we can say that the acceptable value of c is minus 2 plus square root of 2. So this is the required value of c, which verifies Rolle's theorem. Clear? Actually here we are getting two values of c, and Rolle's theorem says that if a function satisfies all these three conditions, then there must exist at least one value of c at which the tangent is parallel to x-axis. So here we have obtained actually two values, but this value does not satisfy the conditions of this Rolle's theorem in this interval. So the only acceptable value of c is minus 2 plus square root of 2. Clear? Viewers, let us take this problem. Here we have to verify Rolle's theorem for fx equal to x minus 1 times x minus 2 in the interval 1 comma 2. Now let us see the first condition here. We have fx is equal to x minus 1 times x minus 2, and it is a polynomial. Fx is a polynomial of degree 2 here, so therefore it is continuous. Clear? Because all polynomial functions are continuous. Second, the derivative of f. So here we have we can express this function as x square. This is minus 2x and minus x minus 3x, and we have plus 2. So here's the derivative of f is 2x minus 3, and this exists in 1 comma 2. So fx is polynomial of degree 2, and it is continuous because all polynomial functions are continuous. So this is continuous in this closed interval. Here the derivative is 2x minus 3, and it exists in open interval 1 comma 2. Thus these two conditions are satisfied. The third one is fa is equal to fb. So here a is 1 and b is 2. So f of 1 is obviously 1 minus 1, and 1 minus 2, this is 0 because 1 minus 1 is 0. Similarly, f of 2 is 1 this is 2 minus 1, and this is 2 minus 2, and 2 minus 2 is 0. So therefore both are equal. So therefore we can say that f of 1 is equal to f of 2. So here's the three conditions of Rolle's theorem are satisfied, and hence there must exist a value of c belonging to ab. There must exist c belonging to 1 comma 2 such that f dash of c equal to 0 or f prime of c is 0. Clear? So f dash of c is equal to 0 means we have to substitute the value of x equal to c here. So we have 2c, it is 2c minus 3 is equal to 0. So we have 2c equal to 3, and c is 3 by 2, and we have c is equal to 1.5. And viewers, it obviously lies in 1 comma 2. Thus the Rolle's theorem is satisfied, and we have one value, that is c equal to 3 by 2, at which the tangent is parallel to x-axis. Clear? So viewers, in today's lecture we have solved some important problems related to Rolle's theorem. In our next lecture we will see some solved problems on Lagrange's mean value theorem. I have already discussed in detail regarding Rolle's theorem and Lagrange's theorem in my previous video. Thank you.